but feel free to grab your drinks and find a space to sit down. And if you can't find a space, please let one of us know. We'll get your chair. So today, we have a speaker who is visiting Japan for about a month. And she's Anastasia here.
Hi,
say hi. And so I actually met Anastasia maybe 10 years ago, and in Greece, in Athens, at a workshop. So it's been a long time. And Anastasia is currently a PhD student at UCL in England, London, and also working, actually her supervisor is a PI of Ariel mission. And so she's a big part of this mission, and so she's going to tell us all about why this mission is important, and why we should know about it, and how to be also part of it. And so apart from doing science, Anastasia does so many insane amount of other things. Like you can bring any hobby and she's, oh, I have done that. So within 1 month in Japan, she has done so many things. So it's very exciting if you have time to talk to her. But I want to share one hobby Anastasia has. She makes perfumes. And like homemade, really cool. And I got to smell some of it in after our last meeting yesterday. And they're really good. So I highly recommend if you're interested in perfumes and smell, talk to her. So Anastasia, thanks for doing this talk today. Please welcome.
Thank you. Microphone, okay. All right, and my presenting stick. Fantastic, thank you. Okay, with a microphone. Hi everyone, konnichiwa. Nice to meet you. It's a great pleasure for me actually to be here. Thank you so much to Lina and Mayuko for the invitation. They're both great friends and colleagues, so I'm doubly happy to be here. I'm a big fan of Japan. I came last May. I really liked everything. So here I am. I plan to come back for sure. So I will be talking about Ariel, but before I talk about Ariel, I would like to just introduce briefly myself after Tilina. So my name is Anastasia, I'm Greek, but I am based in London, and I'm doing there my work and my PhD at UCL. And actually, I can share some more things, because I didn't end up as an astronomer from the beginning. So actually I started as a teacher. I started primary education, I really liked it, but I had a professor that was an astronomer who inspired me, and I got fascinated about space and astronomy, and I was like, this is for me, I want to do that. But still the most fascinating thing was for me to share this with others. And this passion of sharing and presenting led me to do actually something else, which was a bachelor in journalism. And I was practicing my entire thing in a television. I was writing articles, so I got really into understanding how it is to share and what is important, and making stories curious, interesting, igniting curiosity to people. But then still this was not enough, because sharing knowledge is nice, but I wanted to specialize in sharing all the scientific knowledge to people, and that led me to do a master's in science communication in Ireland, which was great because I got the opportunity to know exactly all the things I wanted to learn. Learn all the complexity of natural sciences and how we can communicate that to society. And of course, why it is important, we are all part of it. And guess what? This was still not enough for me. I was so greedy. I wanted to do more. And this led me to do a bachelor in astronomy and planetary science. So I switched completely from, I would say, humanities, social sciences, to astronomy. The reason I wanted to pursue that was because I was still very curious about space and astronomy, and I really wanted to have a holistic understanding of the cosmos around us. So it was really fascinating to share this knowledge, but I wanted to have a deep understanding. And it was a big challenge, I can say, because many people were doubting, oh, how are you going to do that? Like, after all this humanities stuff, you're going to study natural sciences, really? Yes, it was a big challenge, but I'm really glad, and I had really wonderful people around me and the teachers. And this is how I ended up finally doing my PhD now in exoplanets. And actually my research is also quite interdisciplinary, so I'm focusing on exoplanet characterization, but at the same time I have research interests in education, outreach, and I strongly believe that it's very important to combine all of this together. So after this, I hope, brief introduction, we can go into the topic, but I have some cool pictures from so far. Because usually people think that when you're doing a career in science or research, it has to be one way or very specific. You're working in a lab, you're working in an office, analyzing data. Of course I do stuff like this, but I have a lot of other things that I have been doing, and I think this is very important to also communicate to everyone that it doesn't have to be one way. So I have met wonderful people presenting astronomy, sharing that with kids, with different audiences, doing projects with them, but also of course got the chance to be involved in important things like the space mission, which we will be talking now, and it's super exciting. So let's get back, let's ground ourselves here on Earth in our solar system, and we start this presentation about exoplanets from here, our home. Just take a moment to see where we are, and this is the complete image of our solar system. As you see, the sun with the 8 planets. We are there, the only home we know so far, but still, this image got complete very recently. We only knew until Saturn, these 6 planets, until almost 200 years ago. These last 2 planets were discovered very recently. So the invention of the telescope and the use of the telescope was a very big breakthrough in astronomy and our understanding of our position in the universe. So we have this complete image, but still, this is just our neighborhood, right? It's our home. What about other stars? Are there planets around other stars? We see all the time the night sky, and here in Tokyo the sky is quite clear, I can say, compared to London, which is very cloudy. So you have the chance to see all the stars, and people even from ancient times had a lot of curiosity, and they were wondering, are there planets around these different suns that we see above there? And today we know that there are many planets. We have discovered actually more than 5,000 exoplanets. And the discoveries are continuing. So we know that these stars that we are observing every night by naked eye, or other stars that we don't even see with our eyes, have planets around them. And this is fascinating, because until very, very recently it was only imagination. Now it is a fact. And of course, the discoveries are continuing. So we count this year 30 years of discoveries. We started in 1995 with the first discovery of an exoplanet. And as you can see, gradually the numbers are increasing. So today we have really the largest number of exoplanets discovered. And the main method that this is that is doing the discoveries is the transit method. So of course, these planets are quite far away and very small, so the question is how we can discover them. And this is one of the most successful methods. So as the planet passes in front of the star, it's orbiting the star, it's actually causing this dip on the light, and this is the way that we can identify planets. It's the most successful way, because as I said, the planets are quite far. And we have several exoplanet hunters. So space missions have been really important for this journey of discovering planets. Kepler was the most important revolutionizing mission because it discovered more than half of the planets. So it launched in 2009, and as you see, it ended like in 2017, but it gave us really like the big number of planets. This is when we realized that, wow, almost every star in the sky has a planet. Today we have TESS, a very important also mission that is discovering every day new planets. So it launched in 2018 and gives us continuously new planets. And then we will have Plato, which will be launched in 2026, and we'll be discovering more planets, but this time in our neighborhood. So the scope for Plato is to discover planets that are closer to the Earth size, but also closer. So it's really like a journey that is continuing, and we have more and more numbers every day. Now, the question is that we know these planets exist, right? We check the box and we know that we are not the only planetary system. And all these stars in the sky have their own systems. The question that arises is, how do these planets look like? We have an idea about these planets, so some of them can be like gas giants, like Jupiter, Saturn in our solar system. Some could be, of course, like the Earth in terms of size and the composition, so more rocky. Some could be like Neptune, so meaning not only in the size but also in terms of composition, more icy material. But there is also a type of planets which we call super-Earths, and you can see it here. And this is the most, sorry for that. So this planetary type is the most, no, it's going back. Yeah. Okay, so this stick is a bit slow. Okay, so sorry for that. So this planetary type is the most mysterious one because these planets are larger than the Earth on size, but smaller than Neptune. And this is a type of a planet that we don't have in our solar system. That's why it's also it's a very big mystery. And still there are quite many of these planets in our galaxy and from the ones that we have discovered. So we don't know if they are larger versions of the Earth, like rocky with an atmosphere, or smaller versions of Neptune, more gaseous. And we are still, of course, having this question. We don't know. So with different exoplanets that we have been discovering and detecting, we can have actually an idea and an imagination of how these worlds look like. So this is an illustration, okay, it's not a real image, but it's a very nice presentation of different types of planets that could exist there. Some could be like Jupiter, as I said, some could have rings like Saturn, Neptune's, Earth-type planets, or like the other rocky planets of our solar system. So now the question is, do you think that from what we have so far, it's enough to say if a planet is Earth-like planet, Venus-like planet, Mars-like planet? The information we have so far about these planets is the mass, the radius, and the temperature. So how heavy, how big, and a bit about the temperature. And I will give you here a small quiz. We have Venus and Earth from our solar system. These two planets are very close in terms of size, in terms of mass, but also in terms of distance from the Sun. In reality, we know that Venus and the Earth are completely different worlds. The Earth is the only home that we have, as you know, it's very, very life-friendly, while the other one is completely different, it's like hell. So definitely not a place to live, at least for life as we are here on Earth. And the big difference between these two planets, anyone wants to?
Magnetic field? No?
Magnetic field?
Something more obvious.
Atmosphere?
Yeah, the atmosphere, yes, yes. So the difference comes from the atmosphere, right? The atmosphere of Venus is very thick, has a lot of carbon dioxide and creates this strong greenhouse effect, while here we have a completely different composition of atmosphere, and of course not the temperature that Venus has due to this atmosphere. So we know that planets are very complex. Even in our solar system, if we take all the planets, you will see that they are so different. From interior to surface to atmosphere, they have a lot of differences. Even in the gaseous planets, we have a lot of storms and different features in the atmospheres that differentiate them among each other. From the rocky planets, for example, Mercury doesn't even have an atmosphere. Then we have the differences between the two planets, the Earth and the Venus. Mars used to have an atmosphere that's very thin, but even if we go further and further, we will never finish because the interiors are also quite different, and we're still discovering that and exploring what is going on. So the atmosphere is playing a very important role for differentiating the different planets. And the atmosphere is a very, very important window for us to understand different things going on a planet. We have information related to the weather, right? Clouds, and even from here on Earth, we can see the climate is so different in the atmosphere. We can get information related to the geological activity, because the connection between the atmosphere and the surface, but also the interior, is very, very active. So, for example, you can have gases emitted from volcanoes, or anything that comes from the interior is going to be emitted in the atmosphere. And this will be affecting the atmosphere. But also life, right? The atmosphere has all of the gases that we need for life as we know it, and so many other things. A connection between the star and the planet, the atmosphere, and how this is actually interacting. So after that, we know that at least there are many, many, many differences between the planets. And as we said, they are very complex. We cannot easily say, oh, this planet is Earth-like planet or Venus-like planet, because we don't have this information. And this is why we need a lot of atmospheric observations to understand the differences around the different planets. So far we have some observations of atmospheres. So one of them, which I had some interesting examples, is WASP 76b. So this planet is quite particular because it's tidally locked, and that means that we always face the same face towards the star. And there is like some discussion around it and some observations showing that there is a rain of iron. So there is like iron that is evaporating, and then when it's moving on the other side, it's condensating. So then there is another example that I have included here for atmospheres. And come on. So K2-18b, this is a very controversial planet. So this planet has been showing a couple of years ago, in 2018, more than that. 2020, I don't even remember. I was involved in the press release. So initially with Hubble there was water being detected, but now with James Webb Space Telescope we have carbon dioxide, and it's quite still controversial what is going on with the atmosphere. We still don't know. But at least we know that it's the only planet in the habitable zone that has, that we know, that we discovered at least, that has an atmosphere. And that makes it even more interesting, and we want to know what is going on. And another example I have included, there are some, of course, more, but this is also quite interesting. So this planet has, we think that has clouds of quartz. So quartz is a rocky material, so it's very interesting because it's not something that we know, at least here in our solar system or on Earth. And the particular planet is a hot Jupiter, so it's very, very close to the star. And in terms of size, it's like a Jupiter. That is why I call it a hot Jupiter. These are very few examples, though. In order to understand better how planets function, what types of planets exist exactly, and unlock all the mysteries, we need a large, really sample of planets. We cannot say just from a few examples that, oh, this is a type of planet and this category. So of course James Webb is giving us some observations now. It's very exciting, but it's only a few of them. In order to understand, as I said, better how the planets function, we need a big sample, and this is what Ariel will do. So Ariel is a space mission. It's the first chemical study of 1,000 exoplanets. It's going to be launched in 2029. It's prepared by the European Space Agency, and it will be quite like a small telescope, 1 meter, not really like James Webb. But the idea is to cover different wavelengths and identify as many molecules as possible. So it will carry a spectrograph to do that. And the goal is to observe 1,000 planets, planetary actually atmospheres. This is the way to do it. And here you can see how the spacecraft looks like, and it's going to be in Lagrange 2 points, so not in an orbit around the Earth. We want to scan as much as possible of the sky. Now, the main questions that Ariel will try to address is how planets form and evolve, what the planets are made of, the chemical composition, and what is the weather there. So these are the main objectives for the mission, and let's move. So, yes. So, in order to understand, as I said, the different planet types, we need a lot of observations. Here I show you the diagram which is called HR. For those that don't know it, this is a very important diagram in astronomy, in our understanding, because this is where we understand and when we realize how the stars function. This is when we realize how our sun also will predict the future, but also understand how the sun was in the past. And this is when we realize that the sun is not the typical star that in our universe, but there are so many other stars with different temperatures, different spectral types, and that's why this diagram is very, very important. We could really understand what is going on with our own star as well, not only in general. But we needed thousands of observations of stars in order to create this diagram. It didn't come like that. And this was also another big revolution in astronomy and science. To do the same with planets, a planetary HR diagram, we need thousands of observations of planetary atmospheres. So that is why it is very important to actually observe many planets and not just stay with a couple of them, or 10s or even 50s, because we want to get the same diagram. But planets are much more complicated, as I showed you before, because they have all these different features and the atmospheric conditions can be very different. But also, the history of the planet can be very different. So I have like a graph here, which will seem very, very complicated. But okay, so these two diagrams, both of them are from the Ariel space mission, the Red Book, as we call it, so you can also find them there. But this is kind of visualizing how complicated a path of a planet can be. So we start with some planetesimals, small rocks, and then eventually this material will be built up, but we don't know exactly what is going to happen. So a planet can actually be on a size of the Earth, but then what it will define that it's going to be like Venus or Earth or different or like Mars. So a planet can lose its atmosphere, can gain a new atmosphere. It's a really like unique path for every planet. So we need a lot of numbers in order to start saying, okay, the planetary history even for our solar system has been in that way. This is, as I said, a very complex diagram. It's just a visualization of what we envision to do with Ariel. And of course, apart from the objectives and the results, sorry.
Okay, let me know.
Yeah. So, which planets is Ariel going to observe? First of all, many planets are being discovered now from the TESS telescope. Okay, so in the first phase, Ariel will observe 1,000 planets in more like a basic level. Then it will focus on the second phase on 600 planets, and then it will do a much more dedicated study in the third and final stage of 50 planets to understand even more what these planets are made of. So it will start with 1,000 planets, but then it will do more focusing study of the 50 planets. This is the QR code with all the mission the mission candidate sample, so you can find more information about the planets, and this is continuously updated based on the new discoveries that we have. But also apart from the candidates of the mission and all this work, come on. So, we have a big team. The Ariel team consists of 600 scientists and engineers coming from 16 European Space Agency countries. We have also a NASA contribution, but also a JAXA contribution and participation, the Japanese Space Agency. There are 22 working groups. So we have groups working on different things, from the data analysis to the scheduling, to the interior of the planets, to the chemical like evolution, to anything you can imagine. So we have a lot of different working groups, and the mission is quite interdisciplinary because we cannot focus just on one aspect. And we have a group that's working on the stars, because we have to identify the parameters of the stars of this planet. So it's a really, really diverse mission. And I want to say that it's very important to have international collaborations, and that's why also the mission is quite open. We had recently our consortium meeting in Lisbon, so you can see, you can get an idea of how big a mission can be, and it keeps growing, of course, because the mission is quite open to participation from different people and communities. And this is actually also something that the mission tries to enforce more, to have an open approach and policy and aspect. So the mission in the consortium, we are actually using all aspects of open science. So open science means not only open data, but also open software, anything related to contributions. So open science is very important because we can also encourage more discoveries, but also allow reproducibility of the results. It's a very important idea to have when you're doing science. So yes, we are open. That means that anyone can be part. So apart from that, the mission started already having an open policy. The data will be all open after the first check for the first round, the demonstration, and then in the operation phase, we have different also policies, but everything will be open as you see. And there will be also some extra time for other science, of course, and this will be through some special calls. But the software and anything we're using also is open source. And because I said that the contributions are very welcomed in the mission, so in this data analysis group, yes, we have the Ariel data challenges. These are open to everyone. So every year there is a data challenge. You can see the QR code here, with a prize of $50,000, if this is motivating to you. And the idea is to use artificial intelligence to solve a problem related to the mission. I can say that this year there were, as you see, more than 23,000 submissions. When we say submissions, they are coming from everyone, from university students, just amateur people that want to experiment, professional coders or people that have like an experience. This year, the first winners were from here, Tokyo, University of Tokyo, coincidentally. So very, very interesting. And every year there will be a new one. There are also like trainings going on to support people that don't have a background. And if you're interested, you can have a look on the QR code here. So apart from the data analysis and the challenges, the mission will use the method of spectroscopy mainly. As the planet passes in front of the star, we observe different wavelengths, different colors in order to identify the molecules. And this is also where my role comes, where we have another working group. We switch from the data analysis to the scheduling, the preparation of the mission. So, okay, yes. So observations are very time critical. You see that Ariel will observe one planet after the other, so it has to be very, very precise because we have the transit phenomenon, but then we have this planet where we miss the transit. Why? Because we didn't have a good scheduling, we didn't have an accurate estimation of the timing of this planet passing in front of the star. This is what we call the ephemeris. And my main role in the mission is to maintain the ephemeris of these planets. So you see in the example of planet A, everything perfect because the transit was in the correct time. But in planet B, unfortunately, we missed half of the transit because we didn't have a good estimation of the planet ephemeris. And imagine that we're talking about a space mission, so time is very important. That's why we need a good scheduling and a very precise timing for all these planets. We're talking about thousands of observations and 1,000 planets. So most of the telescopes that are discovering the planets, they don't continue observing them because their time is very precious. And this is actually where we initiated with my co-coordinator, Angelos Tiaras, this project which is called ExoClock. So ExoClock is, as the name says, clock. We are monitoring the timings of the planets. In order to do that more, I would say, efficiently and in an open way, we created a project in a very open science way, so anybody can participate, not only professionals, but we have a lot of amateur astronomers, citizen scientists, and schools. So as you see, the idea is to connect our power with different small telescopes coming from different parts. So we have participants from all over the world. And this is a website, it's open if you want and you're interested to have a look. It's a database. We are directly giving the results to the mission for the scheduling. And that's why we are one of the most active working groups now, because we have to ensure that Ariel will observe everything in time. So the project is very inclusive. As the mission is, the project is also very inclusive. And we have professionals, amateur astronomers, university and school students, but also people that don't have any background, citizen scientists. And the observers really vary. These are some examples of telescopes that we have had participating and joining. Really, any telescope that you can imagine. It can be a very small one or a larger one. But the idea is to make the most out of these telescopes and make them useful for a big science mission, which is Ariel in our case. So, of course, the project is open for you too, if you're interested to participate. The project is very interactive. We have meetings. So we are like a small consortium meeting. We have, we give trainings. We have newsletters. We meet very often. We do even an annual meeting. So it's a very interactive community. I think now this is more like 2,000 participants because we had a new campaign and more people joined. As you see, most of them are amateur astronomers coming from different countries, 70 countries. Then they have provided 10,000 observations, which is incredible. Imagine a small telescope giving an observation that will become useful for a space mission. And all these people become co-authors. So the idea is to make them feel part of the community, but also acknowledging what they're doing. In the new paper that will be out soon, we hope, we had 620 planets that we updated, and actually 40% of them needed an ephemeris update. They needed to be observed, which means that we should continue the monitoring. This paper will have 350 co-authors, which shows how people are motivated. When we started the project 5 years ago, we started with 50 authors, then 120, 220, now it's continuing. What I like in this project is that people with even zero background can become part of it, and they're getting very motivated to contribute to a space mission. So I think this is the biggest thing for them, that they can become valuable for something that is so big. Having a small telescope is nice to observe the night sky, but then it's fascinating how much people want to understand the methodology behind it and then do something so valuable. And we had our annual meeting in Lisbon just before the Ariel consortium meeting. So most of the people that you see here are either students, amateurs, or a university, or even we had a couple of citizen scientists. It was also online, so you see only a small number of people joining. But the interesting point about this meeting was that it was right before the Ariel consortium meeting, so we had the opportunity to connect a lot the amateurs and the citizen scientists with the people from the mission, and showcasing that a space mission can indeed be very, very open and also inclusive. And it was really nice to see the scientists from the mission talking with everyone and exchanging knowledge, but also opinions on things. You can join us. This is another way you can join us. So I talked about the Ariel data challenges, but this is another way that you can join the mission throughout this working group and the ExoClock project. And of course, this is if you have a telescope. If you don't have a telescope, because we thought also about people not having a telescope, you can still be part of the project. So no telescope, no problem. We have ExoClock unlocked. For those, that's a very interesting point, because throughout the years we have had people saying, "Oh wow, that's so cool! I want to participate, but you know what? I don't have a telescope." So we initiated this project where you don't need equipment to participate. This is the call. It's like a small course. We collaborate with Las Cumbres Observatory that they have remote telescopes, so they give us some observing time, and together we create a kind of a course where people learn from zero background how to do an observation, how to analyze it, and then they become also co-authors in the publications. So I can say that this has been a very interesting journey, because when we started the project, we never thought that we will have people without telescopes, right? We started for people that had telescopes so they can become useful. But it's incredible how still people want to learn, and they can become very, very useful, because we observe planets that are also very, very difficult to observe with this observing time. So this is another way, and I think it's interesting also for people that they don't have anything as a prior knowledge. And apart from those, we have also a strong connection with schools. So we have very interesting projects that schools can take part. This is an example in the UK, but every year we have been running in several countries. So actually, the students participate from zero again. They analyze, they schedule the observation, they analyze the observation, and there they're getting acknowledged. And then they will deliver a certificate of participation, which is very exciting for them, because it's signed by us and the PI of the mission. So I think this gives them even more motivation to become part, and they know that if they do the entire project, they will receive that. Which from one side is very nice, because the students can get the opportunity to have a hands-on experience, and from the feedback we have had so far, what is important for them is that they have a real experience of how it is to participate in science, but so interactively, hands-on. They are doing everything, they're taking the decisions, of course with the support and all the proper requirements, but they will have the opinion, and they know they can learn from their mistakes, but finally they will see the results submitted, uploaded in the mission, published, and they can also use that for not only for their learning experience, but also for their curriculum vitae. We have several inspiring stories where students got into the university from underrepresented areas through and by having this in their curriculum vitae, which for me is the most important acknowledgement. So very diverse, as you see, and of course if you are a teacher, you have a connection with a school, you're welcome to join. And somewhere here I think I want to sum up, because I want you to have also the opportunity for questions. So Ariel, we study 1,000 exoplanet atmospheres, so we can better understand what they're made of and create what we envision as the planetary HR diagram. This diagram will help us also understand our own home, the Earth, how it fits within this large universe, but also our solar system and how unique or different is our solar system. The mission applies open science policies in different ways, as I hope that I showcased today, not only to the professional communities, but also to different audiences, as I said, amateurs, but also schools and anyone. There will be an Ariel Open Conference next year. It's planned for spring 2026. And these open conferences are again welcoming anyone interested to learn or also participating in a more active way. It will probably be in Harwell in the UK, but stay tuned if you want to actually get part and become part of it. So here I will close with some QR codes where you can learn more things. This is my personal, but then I have also for Ariel, for the mission in general, for the social media of the mission, and separate links for Exoclock and the educational things related to Ariel. And I couldn't finish without appreciating our planet, because this is my favorite planet actually, the Earth. Yes, I get really curious about other worlds, but still planet Earth is my place to go. And I think something completely different, random. I'm doing astrotourism in this island, which is called Ikaria. You're welcome to join. If you ever come to Greece, please join us. It's a fantastic place. So this is the QR code, but it's an ancient amphitheater, so we combine the Greek mythology with stars. And of course, if you come, remind me that we met in Tokyo. And I think I will end up here. Let me go back to them. And thank you.
Thank you so much. So we all have to go to Greece. All right, let's take some questions. Let's start from here.
Hello, Ellen from Nelson.
Like a conference.
Thank you
Is
so
this going to
much.
be a thing?
Yes. Thank you so much for this talk. This is so awesome. First, I want to say thank you so much for giving opportunities to young girls to explore space science. Like, I know we've connected so much on that, and so I'm so happy that you're offering that opportunity for young girls to get involved. I did have a science question. So in terms of the planets that you are actually watching or doing the transit observations, we know that most stars have more than one planet. So how are you guys determining which planet you are targeting? Is it just based on happenstance, or is there a way that you're picking which transits you're trying to catch? Can you talk a little bit about that?
Yes. Are you talking about the space mission or in general?
For the mission.
So first of all, we are going to observe planets that are definitely confirmed planets. Okay, so we have several planets that are being discovered, but they are candidate planets. We are aiming for planets that have several observations behind. Now, there are systems that have multiple planets, but again, they are rotating around and orbiting around their stars in specific timings. So the transit is a periodical phenomenon happening in every, let's say, for the period of the planet is 3 days or more. We know that, we track that. So we have a good idea of if there is like a multiplanetary system when this planet is going to observe. This is known. What is not known, many times we discover even new planets, and this is an interesting point. So we have an idea. What we are missing, as I said, is the very precise timing, and many times there are a lot of errors also. So depending on the period of the planet, we know, and of course we keep discovering, even in known systems, more planets. This is how they are like B, C, D, E. Yeah.
Can I just ask, so with the study, you start with 1,000 and then it was 60 and then 50 or something like that?
Yes, 600, yes.
Oh, sorry, 650. And I was just wondering, like, how do you, what sort of criteria are you going to use to narrow that down? And then what additional things are you then going to check in each phase?
Yeah, very interesting. So the first stage is actually quite explorative. We want to, first of all, see the planets, have a pretty brief, I would say, idea of what they're made of. So then, depending on what results we will get, the second stage will focus on the most interesting planets, which we cannot know from now because it depends on the first round. And then the plan for the really focused ones will be to track planets with very interesting climates or weather conditions in order to actually specify which phenomena are happening in these atmospheres. Because if we observe, when we observe like 50 of them continuously and having a good monitoring of these planets, we can really have a good idea of the specific phenomena. Like if there is something affecting us, even from here on Earth, you need continuous monitoring. We have continuous monitoring, so this will require more an in-depth investigation. But I can assure you that many of these planets are not even known now because they're being discovered from tests, and this is also another thing. So definitely there will be a review every time. And something else, there are some objects that are called brown dwarfs, so we'll have also observations of objects, not planets, that are not stars, not planets, which are very mysterious, also very, very like different.
Thank you.
So, is there a practical application of studying exoplanets, like, for instance, exploring our own planets and moons in the solar system, like Mars, Saturn, and Jupiter, how to colonize them?
Oh, to colonize them.
Well, yes.
Yeah, yes. Actually, yes, the idea of, in general, of studying exoplanets is to identify the different types of planets, and this knowledge then can be used to better inform the knowledge about our solar system planets. So I don't think we have reached the stage of thinking and this is not also, I think, the perspective here, but it's more like understanding better a position and how we ended up having this solar system in this way, in this architecture, like starting with this star, and then why we have first Mercury, then Venus, Mars, and so on. The 8 planets, is it that common in other planetary systems? And then we can take this knowledge to understand why we ended up like this, or if we are very, very particular and very unique. So this is something that we don't know. So in terms of that, we have this reflect between exoplanets and our solar system, and there is also a synergy around the two. We have a working group that is doing exactly that, taking all the knowledge from our solar system to apply it in exoplanets and all the way around. Anything that we observe particular, interesting, that remind us the planets of our solar system, applying this knowledge to better understand what is going on. I don't know if I answered.
Well, yes. So it makes it. We understand what are the issues in, saying, going to visit Mars, Europa, etc. Those and seeing what are the issues, the problems on because of the atmosphere, the gravity, etc.
For sure, any of the planets, any planet in our solar system can be considered as an exoplanet. And there are several studies, or the moons, like because there are several planets that are so far away from the stars that they will be like an icy planet, so completely made of ice. Or planets that are so close to their stars and they're pretty much made of lava because they're continuously melting due to the high temperatures. Now this is something that you're raising, I think, quite futuristic, but at the same time
Well,
We could not.
but
of course.
Elon Musk wants to colonize Mars, doesn't he?
Yeah, well, Elon Musk has his ideas. let him have his ideas. I mean, in terms of distances, we are opening a big topic where personally I don't think that is a good idea to colonize. But, okay. Yeah.
So my question is kind of building on that. For example, if a star is, let's say, bigger than the sun, would finding a planet like Earth, would you kind of look in proportion to the distance from what the distance of Earth is to the sun? Like how would you kind of go about looking for planets which would be more likely to be habitable by by a life that is similar to us?
Okay, I don't know if I understand your question. So you're asking if we are looking or how we are looking?
So if we are looking for life like
Okay.
us in like a different exoplanet, would you how do you kind of look? What kind of like exoplanets or how far away from a star? Like let's say if like a star is bigger than like our sun, then would you look at like in proportion to like let's say Earth distance to our sun is X, so would you look at like 2X or something like that?
Okay, so let me try to put some things into context. First of all, we have very limited knowledge and very limited information in general that we can get related to life from exoplanets. As I said, these are very far away, very small. We have very limited techniques. So the transit spectroscopy is actually the only way that we can have a better idea or more information about what is going on inside these planets. It's not even inside, it's the atmosphere. So as we saw, there are many layers on a planet. Anything that is in the atmosphere, right, can give us information related to geological processes, interaction, the weather, but also if we have some biogases, we can think about life on these planets. However, it's not that simple, because even from the Earth's spectra, we have a very specific spectrum that is showing that this is life. This is not easily detectable actually with the current tools and techniques in exoplanets in this amount, and of course the amounts of the gases that are on Earth, okay? And also you have to be very careful because there are many errors many times when you observe an exoplanet spectrum, and there is a degeneracy. So for example, as I showed with K2-18b, we identified in the spectrum water, but because many times you have a lot of noise actually in these instruments, coming from the instrument but also from other resources, we are limited. So now James Webb, which has a better capability, it shows as carbon dioxide, which is still controversial because we don't know if this is still the truth, right? And we need more observations. So I'm trying to disentangle your question just to show how many steps we have to follow and then to decrease the errors, right? We need a lot of observations, but then also our detectability is very, very limited. You mentioned about the habitable zone. Yes, so this is the first stage, and that's why there was a big press release a few years ago about K2, because K2b was known to be, and it is, in the habitable zone, so the correct distance from the sun, the star, and then this correct distance allows water in liquid form. That's why we are getting really fascinated, because this is how we know that life operates on Earth. Okay, we need water, liquid water, and then everything else. Okay, but this is only one thing. We don't know anything else. So yes, it's a step closer to understand, and I'm looking for these planets in the habitable zone, of course, and then looking for the gases, but doesn't mean that there is life. And even from our solar system and the Earth, we know there are so many other conditions. It's not only about the distance. As we saw with Venus, I will remind you Venus, that is very close in distance and size, but It can be considered as habitable zone, part of it, the Venus habitable zone, but it's very different. And why a planet will follow one on another path, this is a big story and a big mystery actually. Yes, so we need to be very careful when we talk about, and when you read also about what is life, and then just the gas means there is life. And as I said, the spectrum of the Earth, have a look, it's very specific. Might be able in later on through some ways to identify, but doesn't guarantee life also, so yeah.
Let's move on to the next question. In summary, there'll be plenty of work to be done. He can still do a PhD.
Oh, for sure. And we have also an astrobiology working group, by the way.
I might have missed it, but how exactly do you determine the gases from an atmosphere without, and maybe I don't know this, but without losing the power that you have to go through space?
Oh,
And the atmosphere would bring you down. How do you?
so most of the atmospheric observations are done with space telescopes. So we are out of the Earth. We don't have the obstacle of our own atmosphere. We are continuously observing when it's transiting, and then it's filtering throughout the star's atmosphere, we can say it. So then through that we can observe in different wavelengths. I showed a slide, I think.
Yeah.
So every wavelength will correspond to a different molecule, or then it's a combination of features. That's why many times it's very triggering and challenging. If you have one feature, it can overlap to different.
Okay.
That's why you need also many features, a combination of features. So it's like barcodes, if we can say, yeah.
Thank you very much.
Okay. Let's start from here. Last few questions.
So you explained that the rationale for the Ariel mission is to make like an HR diagram version of the planets. So I believe that we need to like understand like the age, the age of each planet. So like how do we like estimate like the age of the planets? Are they like I don't know, similar to the age of its host star, or could they be drastically different, like quite younger compared to its star?
Yeah, very good question. So everything starts from the stars, actually, right? So we have a working group that is also very active on the stellar determination, characterization of masses, ages, anything related to stars. And of course, if we have a good idea of the star, then we can have a better idea also of the planets around it. And it's also about the chemical evolution. So every star will have different abundances, if we can say, ratios of the chemical elements. And from the HR diagram of the stars, we have a good idea of how this is gonna be. So that's why it's we can't do the HR diagram of the planets without the stars. We start from there, we have a good idea and predict how a star will evolve, and then this will help us understand also the planets. But you're right, it's very important, and that's why we need more observations. And maybe to construct a very detailed diagram, we will need even more missions.
Yeah. Thank you.
Thank you. So, from a technical perspective, how long is Ariel expected to last once it's shot out? And also, in terms of your specific project, when you're trying to do the timing of the transits, I would imagine that as you get further away from Earth, it might be trickier to make sure that the timing is still working out if there's a communication lag. So is that being taken into account?
So first of all, Ariel will last, it's expected to last 4 years. This is the lifetime of the mission. And then depending, always, it's with the missions, but this is what we expect. Now, for the timing, just to clarify that we observe from the ground mostly. We have some space telescopes, like I didn't mention a lot about it. And we are observing a planet that already has a known ephemeris, but is not accurate. Okay? So with continuous observations, we can actually collect this data together and update. So when you have many data, you decrease the errors. This is what we're trying to do with the timings. Because initially they have a big error. So there is not really about the communication line that you mentioned is not really related, but yeah, I don't know if it's clear. Yeah.
One question more on the technical side, or more exactly, thought hypothesis. Let's imagine we are observing something like a Jupiter system.
Like
How much
one Jupiter around the sun?
one Jupiter with all the moons?
Okay.
What would be the impact of the moons in terms of pollution and the discrepancy in the data
Yeah,
about this
exomoons.
atmospheric characterization? Is it insignificant just because of the difference of scale between the main planet and the moons, or could they create these significant discrepancies?
That's an interesting question. There is some work going on for exomoons, but the signals are so small and little that we haven't actually managed to completely identify and kind of detect the moon. There are like studies that say they have detected or they propose, but it's very uncertain because the signal, imagine if the signal of the planet is so small, but there are some ways, like when we have, we call them transit time variations of the moons, so like dipping, we have differences in the time as they pass. It's really complicated, it's really complicated. Now if it's going to affect the atmosphere, this is, I think, ways too far, but I guess there is an area for work also, yes. It's a bit, again, further away because, as I said, even the signal is very small now. Now for the atmosphere, it assumes that the moon has an atmosphere. It's like a long process.
Yeah.
Okay, we should take the last question from the back.
Yeah, how much of a difference or an impact has artificial intelligence had on the observation and interpretation of the observations in the last few years? How much has it accelerated your work?
So I can say that in terms of actual observations, artificial intelligence can help a lot with improving the results and the identification of the different features. I'm not the expert one to talk about that, but I know for sure that there has been a lot of development and evolution. But we will not know until we have the data actually, because now it's only simulations. So in order actually to say how much impact, to quantify it, we need to wait until the data are coming. Now it's only simulating data. And there is impact, but I cannot, I'm not in the position of saying how much impact. We need to have the first round of data with the chemical.
Right, great. Thank you so much, Anastasia. Okay, so thanks again for that wonderful talk. And so we are here at Good Heavens Pub. Michael, can we go to the next one? Yeah, so we are here at Good Heavens Pub. We meet sort of like once a month, and they're hosting us for more than 6 years now. And we are not the only one here. Actually, there's plenty of other events going on. If you can go to the next one. So in February and March, there are a bunch of events at Good Heavens. There's of course famous Sunday roast going on here. And I don't know if anybody watched Super Bowl? Nobody? Few people. No treasure. And I think so. I don't watch Super Bowl, but I think this is the one somehow Taylor Swift is linked to, right? Okay, that I remember. So if you want to watch Super Bowl, screening here, and there's also bagpipe night and a live music, and then there's a 80s night in March. So you have to get dressed to come here, and feel free to buy some drinks and food and support them. Next. Okay, so some of our colleagues at RIKEN is one of the famous research institutions in Japan, and they run this blog for, I think it's kind of for top public and bit of science enthusiasts, and they cover pretty much the research they do at RIKEN. It's a very good institution. And they also cover some things happening, people are sharing at Space Cafe. So feel free to look it up, and there's a QR code as well. Next. Okay. Unfortunately, I'm going to miss this, but I highly recommend to go to our sister event, Nerd Night. And it's going to be on February 21st. The format is a bit different. They are basically a bunch of nerds talking about the things they love. And so some of them are science, but not everything is about science. So there's 2 speakers this month. One is about open source fern. Fern is the tree. And yeah, don't ask me what is open source fern. So you should go and figure out and tell me, because I can't join. And also next month we will meet again here. We don't have information yet, but hopefully within next week we'll sort of share. Next. Okay, so Space Cafe is organized by Ken here at the entrance that everybody met. Ken is at University of Tokyo, and then Maiko at the back. She's at Tenmandai in Mitaka. And then we have Chase, who's running around and taking all the photos, and plus a video that you can see all the lectures from the past. And my name is Tilina, and I work at Earth Life Science Institute, and which is also where Anastasia is visiting for a month. That's us. So, is there anything else? That's it. Okay, we can go back. So, thank you again for joining this month, and hopefully we'll see all of you and more next month. Thanks.